Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson, we are looking at separations, and in particular, we're going to look at the equipment necessary for doing absorption or stripping or distillation. So the internal construction of a distillation tower is going to depend exactly on what we're putting inside, obviously, but is this a trade tower or a packed tower? And we want to look at some of the options there. Trade towers can have several different sorts. So these are pictures of what sieve trays might look like. Essentially, they are just holes with perforations in them, but the edges are cleaner they're better than just really straight holes, but essentially it's just a tray with holes in it. And it allows the liquid to pour down, and the gas can then bubble up through those holes. Valve trays are a little bit fancier because those holes are covered in various ways with valves that allow the gas to push up and into the liquid and go through, but then minimize or eliminate the ability for the liquid to fall back down through those holes. Bubble cap trays are going to be fancier still because they have little lips on them so that there's always going to be a certain amount of liquid available on the tray. But if you look at it here, the gas would come up through that hole, and then these covers, it would come back down. And so it encourages good mixing, but it's also, you're going to pay the price of higher pressure drop. There's all kinds of packings that we can put in a packed tower. So some of them are going to be Rashig rings, burl saddles, Paul rings, so many different types. They can be made out of metal, plastic, ceramic. All sorts of varieties of packings are available. We also have structured packing. So the other variety was random packing. This is structured packing. I think these look like the old Brillo pads that we used to use for cleaning our cookware when we were camping. But essentially they allow for flow, and because they are bound together in a way, the flow patterns are more regulated. Now, when you're designing for tray towers, basically the idea is that the tray has a layer of liquid on it, and then that's going to spill down over downspouts onto the next tray. And then gases bubble up through the bottom of the tray to mix with the liquid. So either through those sieve holes or through the valves or through the bubble caps. And that's going to allow it to come to equilibrium at least certain locations or near equilibrium. Now, some of the problems that happen here, many different things, but the ones that really we are concerned with, foaming, first of all. Foaming means that you are carrying some of the liquid up with the gas to the tray above. This mixes the compositions, and so therefore you're not going to get the behavior that you were expecting because you are artificially bringing some of the liquid from a lower tray to an upper tray. Coning is when gas forms an opening in the liquid. It blows through so fast that it actually just leaves a hole there. That means you're not getting that good mixing. You're not going to get that near equilibrium situation. So coning is also to be avoided. Weeping is when there's not enough gas flow, and so the liquid is allowed to come back down through those holes that were intended for the gas. And dumping means the liquid just doesn't even really reach the downspouts, and so then it goes until it fills up, and then it all comes over at once, and then the level goes down and it fills and all dumps all at once. Now, as we're doing our design, we're going to need to specify quite a few things to get to where we have an actual physical design of our trade tower. So we're going to need to know, of course, the number of trays and where the feed's going to be and what the reflux ratio is. Those things we learn about in our separations class. We also need to know the heat transfer requirements. So how much heat do we have to add at the reboiler? How much heat do we need to remove in the condenser? What's the diameter of the tray or the tower? And that may be different for above the feed and below the feed. We also need to know about the spacing between trays, the hole size, especially if we're doing sieve trays, and what the spacing is going to be for those. What's the pressure drop per tray? What's the tray efficiency? And is there going to be any predicted weeping or entrainment involved? For packed towers, the idea is quite similar, except for instead of the liquid and gas mixing on a tray, they are spread out over packing. And the gas has to come up through there. And so the packing, the job is to give a larger interfacial area where the gas and the liquid come together. Now what's going to happen is you end up with a continual change in equilibrium composition as a result of this. Some of the things that you need to think about are going to be whether or not you want random or structured packing. Random packing is going to be cheaper, but it's going to settle over time. It's going to cause channeling, which we'll talk about in a moment. It has some operational issues. But if you're going to be going back in for maintenance fairly often for other reasons, then random packing is a great choice. Structured packing will be more expensive to install, but you don't have to do the maintenance as often. So that will be your choice. And you need to verify that the weight of the fluid isn't going to crush the packing. There are various ways of dealing with this, but it is an important concern. And operational issues we need to worry about here are channeling and flooding. Channeling is when, so all the surfaces on that packing need to be wet in order for it to be as effective as what you designed for. So you may need to distribute the liquid. So you'll have like downcomers that distribute the liquid across the top of the packing. And then about every 5 tower diameters in height, you'll usually have a break in your packing and then another opportunity to redistribute the liquid. And the advantage of that is that it minimizes regions where you have just liquid just pouring down and no gas coming back up through there. You want to select particle diameters that are smaller than the tower diameter over 15, and frequently they are much smaller than that. Now flooding, the issue here is, you know what flooding is, right? Liquid is coming up. So at the load point, which is the limit where flooding is just about to occur, the liquid starts to accumulate and the gas is still a continuous phase, but you do have liquid beginning to accumulate. As the gas velocity decreases, the liquid is going to fall through the gas, and then as the gas velocity increases, the liquid will start to accumulate. You have flooding when then that liquid accumulation starts to blow back up the tower. So we think of rising water levels, but it's just the water moving up through the tower. Now, operationally, you'll know that this is occurring when you have small changes in gas velocity that end up with large changes in pressure drop. Normally, we're going to design to be at about 70% of the flooding velocity. When you're doing the design of a packed tower, in addition to the theoretical height of packing and the feed location and the reflux ratio, you also need to, again, know the heat requirements for the reboiler and condenser. You're going to need the tower diameter, the type of packing, and the size of that packing. You'll need a maximum height before redistribution, and you'll need to accommodate that in the tower height. And then you also will need to have an estimate of the pressure drop so that you are properly able to size the flow equipment across this. So this concludes this video lesson. Next, we'll be looking at how we make decisions about separation equipment. Thank you very much for your time.